Hello everyone. In this video, I will show you how to train a small GPT-style language model from scratch and how inference works end to end. What you will learn in this video is following: what pre-training actually does, the core components of a GPT-style transformer model, how the training loop updates the model parameters, and what comes after the pre-training. We will talk about that, but I will cover those topics in details in the future videos. For example, SFT preference alignment such as RLHF, TPO, and other alignment techniques. Pretty famous one these days is reinforcement learning with verifiable rewards. In what scenarios does that work? We will discuss all of that in later videos. But today our focus will be on pre-training. So let's try to understand with help of visualization the modules that we are going to cover in this video. And by the way, this is all of this I have put into a single notebook, which is mostly inspired by Sebastian Raschke's repo about building a large language model from scratch. This is actually a complete book written by Sebastian Raschke, and this is the supporting GitHub repo. And it has all the essential chapters and their Jupyter notebooks that you can run. And this will lead to the training of a large language model eventually. But what I tried to find was a resource or a pipeline that I could use to train a large language models, or at least pre-train it on a single MacBook that I'm using. Okay, so this pipeline in which we are going to cover the pre-training part today starts with the acquisition of tiny stories dataset. We'll download it from Hugging Face dataset library. Then we will use the byte pair encoding tokenizer to tokenize and build the vocabulary. Once we have the vocabulary, we will feed it to the transformer model, the GPT-style transformer. And then we will run our training loop, which is straightforward, consists of forward pass, the cross entropy loss to calculate the loss between the predicted distribution and the actual distribution. And then we will calculate the gradients with the backward pass, and we will use the RMW optimizer to update the weights of the model. And this will run until the perplexity of the model is below some set threshold, so we can stop the training pipeline and use the model weights for inference. So let's head over to the notebook. This is the notebook that I have compiled. All the modules shown here are contained in this notebook. We will start with the environment setup. We will run this cell first. So for training, we are going to use MLX framework, which is optimized for Apple Silicon. However, this notebook also supports PyTorch. So if you want to change the training framework, you can set it here to PyTorch. Otherwise, it is MLX by default, or if it's set to auto, it will prefer MLX over PyTorch if Apple Silicon hardware is found. Because on Apple Silicon, MLX performs better than PyTorch by almost like 1.4 times. So we will set this variable here. Then we will verify the availability of MPS. MPS is basically the GPU in Apple Silicon. It is similar to CUDA in NVIDIA with MPS backend. So we have confirmed that we have MPS availability. We will run the MLX framework compatibility check. And yes, MLX is available and it is going to use the GPU. We'll check how much system memory do we have. We have 48 gigabytes of unified memory, which is more than enough for training a model size like 100 million parameters. We can go much bigger than this, but just for sake of demonstration and show how this actually works, I decided to use a smaller model.
We will set up the project root directories. Okay, this is okay. So this notebook consists of 8 parts, and each part is a separate module as shown here. Now I will run the cells related to data acquisition. This will download the, I've already downloaded it, but if you run it for first time, it will download the tiny stories dataset from the Hugging Face publicly available dataset library. It will download, we'll run the next set to see some samples. Okay. Okay, it has successfully loaded the dataset. We can see that data has like 2.1 million rows for training and 21,000, almost 22,000 rows for validation. So each row in the training or validation is a story, is a human written story collected from different sources. So we will have a look at the samples from the dataset. This is the first row, I think, from the training. So we can see there's a story. One day a little girl named Lily found a needle in her home. You can read it. Similar is the second story, the third, and all the rows from this.
This cell shows us the character and word count per story statistics. We'll run it again. We can see each story on average has 891 characters. So in all the data set, on average, average character count per story is 891 characters, and average word count is 174 characters. We can also visualize it here and the distribution graphs like this. Okay, in the next step we will prepare the data set for tokenization. We will load it in the list separately for training and validation. So you can see we loaded the 2.1 million rows separately into training text, and similarly we loaded the 21,000 validation text separately. Also counting the total characters that we're going to train on. So 1.8 billion characters for training and 19 million characters for validation. So now we will cover the tokenization. So tokenization is a very essential component of large language model pre-training, post-training, and inference pipelines. Tokenization in itself deserves a video of its own because the topic is very vast, but just to scratch the surface, let me explain why we use the tokenization. So these models, these large language models, deep neural network models, or machine learning models, they don't understand the characters or the words directly. They have to be fed with special numbers that are called the tokens. So what we have to do is we have to convert the text data that we are using for this pre-training exercise into those special numbers called tokens. And the algorithm that we are going to use for that is byte pair encoding. By the way, I have added some intuitive examples about tokenization in the notebook. And this notebook I'll be sharing in the public GitHub repo, so everyone can access it and use it for their own learning. So let's see how byte pair encoding works. It essentially starts with individual characters and then merges them and then builds the vocabulary. So for example, let's say we have the corpus or the collection of the words. It's called corpus, consisting of 3 words: low, lower, and lowest. So we will capture the unique words that the combination of those that we can use to form individual words. which is LOWERST and space, because there is space in between these words as well. You can see here. Okay, so now our tokens are based on this vocabulary. Currently our tokens are LOW if we consider the individual characters from the word low, and then similarly LOWER for lower, and lowest is this LOWEST. What we will do is for byte pair encoding, we will count the adjacent pairs. So we'll see how many adjacent pairs are there and what's the frequency. So for example, the L characters L and O in pair occur 3 times, O and W 3 times, W and space 1 time, W and E 2 times. So this is the idea. We merge the most frequent pairs. So for example, LO occurs 3 times. We will merge the characters LO, L and O to form LO string, this string. Now, and then we will add it to our vocabulary and treat it as an individual token. So we will repeat this until we have merged all the individual characters into repeatable representations, aka tokens in this case. So this is our vocabulary, and then we can see, then we can use the tokens from our vocabulary to form these words. For example, low is also one token, LOWER space, and this forms the word lower space, and then lowest. We continue until we reach the desired vocabulary size, or there are no more frequent pairs. This is when the algorithm stops. So vocabulary size is very important in this context. Vocabulary size will have huge impacts on training of large language models, pre-training, post-training, and inference. So I've also listed the vocabulary size trade-offs that you guys can read in details. So we'll initialize our BPE, byte pair encoding tokenizer, from scratch. We'll initialize a simple BPE tokenizer, which is based on the original BPE algorithm by Sandrich et al. We have run this cell. Let's use as, okay, we will use a small sample from the training dataset to train this tokenizer. As we can see, this is training. Okay, it has performed its merges. So vocabulary size is the number of unique tokens in the entire vocabulary that we can use combined to form different words in the corpus. Okay, so we will test the tokenizer. Okay, we will run a sample text string through the tokenizer. The input is, once upon a time there was a little girl named Lily. The encoded numbers are, and these are the tokens. So once we get the individual tokens in the character form, we assign them numbers based on their order, or there can be other mechanism, but these numbers, let's say, are assigned based on the order. We assign first token the number 0, and then subsequently we assign them numbers until we assign the whole vocabulary different numbers, and then each token is represented by the assigned index in the vocabulary. So we can see that the encoded representation is this 352, 478. These are individual tokens. The individual number of tokens are 12, and then when we decode it, we get the same sentence that we encoded originally. Okay, we can see the sample vocabulary from the tokenizer. Okay, so token number 256 is E and space, consists of 2 bytes. 257 D and space 2 bytes, and then there are 4 bytes as well, T, H, E. This is the byte representation. Each character is 1 byte. So this is why it's called byte pair encoding, because it eventually deals in the bytes. So T is 1 byte, H is 1 byte, E is 1 byte, and then the space is also 1 byte, in total of 4 bytes. And then there are different samples from the same token vocabulary. Okay, now we will use the tokenizer from the Hugging Face that we will eventually use in the pre-training and inference as well. We will run this cell. We will initialize our vocabulary size of 16,384, which is a very decent vocabulary size in practice for training small models. We will run this cell. It will load the existing tokenizer from the directory. We will use the text, sample text, to check the tokenizer. So originally, this is the input. These are the tokens that are formed. These are the numbers assigned, IDs assigned to the tokens. And when we decode these IDs, this is the original sentence that we get. Same with the other example. Now we will initialize the tokenizer wrapper class. So tiny stories tokenizer class wraps the train Hugging Face tokenizer with convenience methods for our training pipeline. It will have different methods that we will use for encoding, decoding, and getting the vocabulary size. Very useful for training large language model. Okay, now we have some special tokens as well, and these are called the EOS token, the padding tokens, and the unknown tokens. So for example, if some token is not known, it is replaced with the unknown. If some token is not part of the vocabulary, it is replaced with the unknown. This token here. So end of text tells the model that the input ends here. Padding is assigned to make the sequence length same for all the inputs, and unknown, as I've already told, replaces the unknown tokens. We will run it. Okay, for EOS token, we assign the ID of 0. For padding token, the ID is 1 in this vocabulary size. Now comes the section about the model that we are going to use for training. So let's see what we have. We are going to use transformer model. Now the transformer model in itself deserves a video of its own because it's a very detailed topic in itself, and I wouldn't be doing justice to it if I were to explain all of it in this video, and this would make this video very long. But to cover the essentials, so transformer basically transforms one sequence of input to another sequence, which is an output, hence the name transformer. So transformer introduced two key components or benefits over the existing models at that time, which were RNNs and LSTM for most NLP tasks. Number one is the attention mechanism. So attention mechanism is what actually revolutionized the whole industry, and the field of AI in general. So what attention means simply is how much important for a given word every other word in the corpus is, or in the sentence, or in the whole input is. So for example, let's say there's a sentence, it is raining outside. Okay, so our token or the word to focus is it. Now what attention mechanism will do is check how much important is the other word to the input word it. Okay, it is raining outside. Okay, so probably is more important to it than raining and other parts of the sentence. So as I was saying, transformer wrote two key things over the existing models. One was attention mechanism, and the other one is parallelization. The computation in transformer architecture can be done in parallel over multiple GPUs and the hardware, and obviously it's scalable as well. And I also mentioned in the beginning that transformer was initially intended for machine translation tasks like sequence to sequence modeling, But then researchers at probably OpenAI figured out, okay, we can only use one part of the transformer, which by the way consists of two parts, encoder and the decoder. The encoder encodes the input and the decoder decodes it into the desired output. For example, we are translating from English to French, so the input would be English sentence, the output would be in the French. But then the researchers in the OpenAI figured out, okay, we can only use the decoder model of the transformer for the autoregressive modeling of the input. Like for example, if we use just the decoder and pass it single token, what it would do is predict the next one just by looking at the previous token. Then we will append the predicted token into the input again, and then pass the whole sequence as an input, and it would predict the next token, so on and so forth. This forms the basis of the inference of large language model. So this is what researchers figured out, that we can use it in autoregressive manner to predict the next token. And then rest is history. We knew ChatGPT blew up, got very famous. Everyone started using it, and that is where the terms like AGI or artificial superintelligence got some mainstream hype, because this was the time when everyone this was the first time an AI model could be used for general purpose, like for example human-like conversation, which was very new at the time. And now the models have so advanced that now they have multimodal capabilities. Not only multimodal, they can also output in different modalities as well. We have text generation, which started with ChatGPT. Now we have image generation, the video generation, and whatnot. And who knows what's going to happen tomorrow. Okay, so without further ado, let's see what we have in the transformer model that we are going to use. So I have added the details of what's happening with the input, how it is passed in the model, and what is computed inside the model as well. So to give you guys a rough idea, so input, we know that input is first converted into tokens, a sequence of tokens. Then this this sequence of token is assigned positional embeddings, because the model doesn't know which token falls where in the sentence. So it has to append the positional information to each token to know what the positional relevance of each token is. Okay, so this is, I'm leaving to you guys to read. I've tried to add as many details as possible. This is the explanation of the configuration parameters for the model. So the vocabulary size we know is 16384. Embedding is hidden dimension. Embedding is the dimension where the whole sequence will be mapped to, the hidden dimension. The number of heads, the attention heads. So what is now used in the transformer is the multi-head attention. So multi-head attention is multiple heads computing attention in parallel. The topic of transformer is well explained in many YouTube videos. You guys can look that up, but if you guys want, I'll make a video on transformer as well, just to explain this concept in details. Okay, now parameter count. Now this is also important. Now you guys must have heard the parameter size of different models that are released. Like for example, this 100 billion parameter model. This is 1 trillion parameter model. The production one, the frontier ones, such as the Claude Opus, that is very commonly used among the vibe coders these days. GPT 5.2. These are trillion parameter models. So parameter, the size of parameters is essentially the amount of trainable weights, or amount of the trainable parameters in the model. And this is also computed in a way, like example of which I have given here. So for example, the model that we are going to use for this exercise is a 33 million parameter model. It has certain number of parameters for embeddings, for blocks, transformer blocks, the final layer norm and LM head. These are the parameters for that 1024. And this number can also be increased up to 60 million parameters just for this exercise, and it will fit the given amount, the amount of memory that we have. Okay, let's initialize the model. By the way, we are going to use MLX for the pre-training, but I'm also using PyTorch just to show the comparison. And there is the flag in the beginning of the notebook. Yeah, I've already covered that part. I think it's here. Yes, it's here, and where we can set the value to choose the preferred framework for training. Okay, so now we will initialize. So in this cell, we will initialize the model configuration. Okay. So we've also added the dropout, so there's not much overfitting on the data. Estimated parameters is this much. Then we're gonna initialize the PyTorch class. The GPT class basically combines all the component into complete language model. This is this model that we are building here is essentially the same as the initial GPT-style models that decoders were released by OpenAI. We will, okay, we have initialized the class with all the essential components of the model. Okay, we have generate function as well. Well, okay, let's create the PyTorch GPT model. Okay, GPT model initialized with 33 million parameters. It is testing the forward pass with random input of this size. The output shape is this. You see the vocabulary size is also part of the output tensor. What we are getting as output is the logits over all the vocabulary. So basically it's the probabilities. So what is the probability that a certain token comes after the input sequence? This is what this decoder model is predicting. Okay, so currently the loss randomly calculated for the random input is 9.840. Okay, test target. It also passed at a randomly initialized test target as well, and then calculated the loss over it. So loss is high, which means the model hasn't learned anything. I'll give the idea that the model is built from scratch. The weights are just initialized. They don't have any information from the data in them. And with the MPS, the memory consumption is almost 1.16 gigabytes using PyTorch. Now we will also do the MLX implementation. We'll initialize the decoder model, decoder part of the transformer with MLX framework as well. Okay, we have initialized the MLX as well. Now let's have a look at the training pipeline. So as I was saying, we use the decoder model in an autoregressive manner for the inference. Sorry, for the training and the inference as well. Okay, so let's have a look at the training pipeline. So what is language model training? So language model training essentially is the next token prediction given the sequence of token. So this is predicting one token at a time. This is what the autoregressive modeling is as well. Given the sequence of token, it predicts what comes next. For example, the input cat, the cat sat on the and the target is the cat sat on the mat. So this mat token will be learned from the data. The transformer will go through all the data, masking the tokens randomly. This is also called masked language modeling. Okay, we in the entire data set, we mask the tokens randomly, use the preceding sequence, as input, and then the model predicts the token that comes next, and the loss is calculated for the predicted and the actual token, and the weights are adjusted. We have better visualization for it here. In the training loop, the sequence is passed. The model output the logits, the token with the highest probability is selected, and then cross entropy loss is calculated over the predicted distribution and the actual data distribution. The loss is then used to calculate the gradients in the backward pass, and then through the AdamW optimizer, the weights are changed. So the next time the model can do a better prediction. This is repeated until the loss is below a certain threshold. So all the details are mentioned here about how the loss is calculated, why AdamW optimizer. So we will quickly run the cells here. Okay, we will initialize the data loader. The data loader should have been initialized before, but I'm making it part of the training pipeline. This will create the data loader class. We will get the learning rate schedule. We will initialize the training config class, where we specify the batch size. The batch size is how many input sequences that we are going to feed the model in a single forward pass. The gradient accumulation step is basically the number of forward passes over which the gradient will be accumulated, and then the optimizer will make changes in the weight after this. Maximum and minimum learning rate for this schedule is also specified here. Warm-up steps with a specific learning rate. So this here, I think, yeah, this part is the warm-up part. This is all done to add stability in the training for the most part. Okay, so once we have defined all the necessary training config, evaluation, and the training functions, we can select the preferred training framework here, which is configurable with the flag that I showed before. Okay, so as I said, I'm going to mainly use MLX for the training, as it is optimized for Apple Silicon, but we will still do a comparison between PyTorch and MLX. Here we can see for the batch size of 8 and sequence length of 256, over 50 iterations and tokens per batch of 2048. The forward pass with PyTorch took 26 milliseconds, but the forward pass with MLX just took 18 milliseconds. So for the forward pass alone, MLX is 1.47 times faster than PyTorch with MPS backend. Okay, now we will basically run the training. So this section is, I think, labeled incorrectly. Evaluation and generation, loss curve visualization, text generation, resampling methods, and attention visualization. Okay, so here we will define some methods for visualization of the training itself. And now we will use the untrained model initialized from scratch to generate some random tokens from an input sample. So this is covered in this cell. We will run it, and we will use the MLX model. So the prompt, the input sequence is once upon a time there was a. So it completes the rest. Once upon a time there was a worms. We see that it is just giving us gibberish. This doesn't mean anything because the model hasn't learned anything from the data. And now we will run the actual training pipeline here. This is again the model configuration repeated, what model we are using. Okay, sorry. So instead of training on the whole dataset, which is obviously going to take a lot of time, we are going to train on a subsample and see if the model learns or not. Because if we see here, before training, the model is outputting gibberish. Okay. Uh, and how many times it is sampled? Okay, I think until the end of sequence is detected. Okay, prompt. Okay, max new tokens here. For 200 tokens, this the whole inference is run on the untrained model, and this is what it outputs. Now let's run a quick training test on a subset of the training data, because if we train it on the full data, it will take a lot more time than I have for this video. So just to prove that the model is going to learn something from the data, we're going to run it. And we can see that it is training, it is tokenizing the data, the subset of the actual training data. And then it is running the training pipeline for MLX framework. We can see with each iteration, the loss is going to reduce. And then the perplexity is also reducing. The perplexity is basically how difficult it is for model to predict the next token. So it is checkpointing the best model weights based on the validation perplexity. After taking a sample from the validation data as input and predicting the next output for set number of max tokens, which is a configurable parameter. Okay, so yeah, to make this training quick, I did it for the subset of the data. And it is almost finished for 200 iterations. We can see that the loss and perplexity have significantly come down from before. And these are the training. This is the training and validation loss curve and the learning rate schedule. We saw this before. This is the learning rate schedule that was applied over the 200 iterations. Okay, we can see how the training loss came down, and so did the validation loss with it. It is going to quickly test the trained model by giving it some sequence of text. For example, it gave it once upon a time, and the model generated the rest. Once upon a time, there was a little girl named Lily. We can see the model has learned from the data. I think it is repeating from the very first story it saw. But now let's try to generalize. And this is the cell if the full training is, if running full training is the intention, then you can uncomment this section of the code and run it. It will run the full training. And these are this is the time it's going to take for a certain number of steps. Okay, now we are going to run the inference. So let's see what's going in the inference. What's going to happen in the inference. Okay, so inference pipeline works like this. It also can be explained separately in another video, how the model inference works, how does sampling parameters work, what does each sampling parameter mean. But to give a quick overview, so let's say we input, we give it a prompt, a sequence once upon, and it is tokenized, and then those tokens are passed to the trained model, and the next token is predicted. The next token is sampled from the output logits. How it is sampled depends on the sampling parameters, and there's different sampling strategies. Those are based on certain parameters such as temperature, top K, and top P. The temperature based sampling usually means that higher the temperature, the more random logits it's going to select, the more random tokens it's going to select, and it is going to be very creative with the output. And if the temperature is low or very or near zero, it is almost always going to select the tokens with the highest probability in the logits. Similarly, top K and top P works on the cumulative probabilities of the tokens. So for example, top K filtering basically keeps the K highest probability tokens. So let's say if we set the value of K to 50, then it's going to select the top 50 highest probability tokens and then sample from those. This again depends on the temperature, what exact token is going to be sampled. And top P nucleus sampling is basically cumulative probability sampling. So among those logits, it's going to select those tokens, let's say 100, whose cumulative probability is 0.9. And then out of those 100, it's going to sample based on the temperature value. So output generation work like this. We have probability distribution of the logits, random sampling. We get our token, we decode it, and then decoded token gets converted into the word. The word gets appended into the input prompt, and then the whole sequence is passed to the model again. And this is the autoregressive inference cycle that we have. We are going to now we are going to run the inference cell. Okay, so we run the training cell again. We will run the next cell, which is this is the inference cell. Okay, so we can try either of these, or we can say there was a little girl named Anna. So let's try this prompt. Let's see what it generates. Anna was so happy, she had a big park, wanted to play with the pig. Now obviously this is trained on a very small set from the actual training data, and it's not going to generalize very well, but we can still see that it learned something from the data distribution it was presented, and it's not outputting gibberish. It is outputting actual words that make sense. Now there can be other issues like with the grammar and whatnot. The output story doesn't make any sense, but these words are at least not gibberish, so this much it learned from the data. So with more steps and with the whole training set, if that is used, it definitely is going to generalize very well. So as a summary, what we did, we learned how to train or how to pre-train a large language model from scratch on a single MacBook. And in the future video, we will cover what comes after the pre-training. We will cover the topics such as the supervised fine-tuning, how to prepare model for chatting, for question answering, and then how to further align the model, how to build the reasoning models from the scratch. All of these topics will be covered in the future videos. I hope this tutorial was helpful. It got a bit longer than intended, but here we are, and see you guys in the next video.